my name is Jason. I'm currently pursuing my Master's of Science in GIS at the University of Redlands. And for my graduate project, like he said, I've been working with the NOAA's DeepSea Coral Research and Technology Program. I'm sure most of us are aware of shallow water coral, but are probably not so familiar with deep sea coral. Now, deep sea coral can live without sunlight because they do not rely on photosynthesis for nutrients. Instead, they rely on capturing nutrients in the water column that flow by it with their polyps. Now, deep sea coral are biologically valuable to us since they harbor other species of marine animals, and they're also economically valuable to us since some of those animals that they harbor are commercially important to us. And furthermore, similar to tree rings or ice cores, their skeletons can be used to reconstruct past climate and oceanographic conditions. Deep sea coral have a global distribution, although their entire distribution is unknown since we have not sampled the entire ocean. Interactions between currents and geomorphic features likely govern the location of deep sea coral as currents move away the sediments and expose hard substratum where coral most coral reside on, and currents also deliver nutrients to these organisms that cannot move. And so features such as seamounts, ridges or canyons that direct and alter current flow have been previously found to be suitable habitat for deep sea coral. Now back to the project. The DeepSea Coral Research and Technology Program hosts an online database called NOAA's National Database for Deep Sea Coral and Sponges. This database contains over 700,000 coral and sponge records that have been curated by the program and is disseminated through this online database that the public can query and download. However, one issue is that this data lacks a standardized naming system for the geomorphic features on which the coral are located. And again, geomorphic features are believed to have a profound effect on the distribution of deep sea coral. And so having a standardized naming system for features like canyons and seamounts will help researchers and land managers develop more effective conservation strategies. And so it was the goal of the project to enrich the coral and sponge data with standardized features. Now, the feature set produced by Greater Arundel and Harris and colleagues fit this criteria since it had a global extent, such as the corals, and it had a standardized naming system. Its features were according to the International Hydrologic Organization standards. And as a bonus, it's hosted by Esri in the Living Atlas, so all of you and its users can use this data for analysis and visualization purposes. This feature set contains 4 base features and 18 smaller discrete features that overlay the base features. And one issue that I'll discuss further in a moment is that the 18 discrete features spatially overlapped one another. Here's a map showing a portion of the base features, which includes the hadal zone, the abyssal zone, the shelf zone, and the slope zone. These features are mutually exclusive, meaning they do not overlap one another, and they are differentiated from each other by their depth and their location to the continent or to an island. Now moving on to the 18 discrete features, I'll name them quickly. These include basins, bridges, canyons, escarpments, fans, goyots, glacial troughs, plateaus, ridges, rift valleys, rises, seamounts, shelf valleys, sills, spreading ridges, terraces, trenches, and troughs. And like I said previously, they spatially overlap each other due to natural transitions and the geologic processes that produce these features. And this is an issue since if a coral is located on an overlap where 2 or more of these features overlap, that coral will be counted twice which violates the assumption of independence for statistical analysis. And to overcome this issue, we performed a union spatial overlay to essentially concatenate the 18 features. And I'll show one example of this in Monterey, which is a popular place for oceanographic research. And on this Davidson seamount alone, there were over 20,000 deep-sea coral records in the database. And here we can see a rise feature. It's overlaid by a depositional fan, which is produced below a canyon system. On top of that, the seamounts, and we can see the Davidson seamount, which is zoomed in here. And on top of that, we see an escarpment, which is a fancy term for an elongated slope, and then a ridge feature. And this location and a location in Alaska was the only two places globally that had this unique combination of these 5 geomorphic features, and these are shown in red, in Alaska and Monterey. And I can't be certain that these features are suitable for deep-sea coral habitat, since the coral data has such a large sampling bias, and the sampling bias arises from the fact that there have been different sampling efforts for different regions of the ocean. But if we look at this orange feature, which is similar in its geomorphic qualities, it includes overlaying escarpments, rises, ridges, and seamounts. There are 45 of these locations, and 3 of them have coral have been present there, and so 42 of them have yet to discover coral. But due to the geomorphic qualities of these locations are potentially good habitat for deep-sea coral, and would be a good place to sample in the future. And one of these locations is in Hawaii, which I'll just zoom into quickly, and hopefully it's not too small. Hopefully you can see this small pink sliver, where there's no coral, but one of these features exists. Now I want to pause for a moment to transition into a second goal of the project, which was to classify seafloor slope position zones for the eastern exclusive economic zone in the United States. Slope position zones are another way to classify the seafloor, and they can be used to further enhance our understanding of deep-sea corals' relationship with the seafloor. Topographic index was used for the classification scheme, and in oceanographic communities, it's also known as the benthic position index. This was developed by Weiss in 2001, and Esri has since then created a toolbox known as the benthic terrain modeler, which can be found on ArcGIS Online, that helps researchers streamline this classification process. And just to go over the process shortly, you use a digital elevation model for elevation values, and you pass a moving window over the digital elevation model to compare the target cell elevation to the elevation of the target cell's neighbors. And this results in a TPI surface where positive values are locations that are higher up in the landscape, such as a hilltop. Negative values are locations that are relatively lower in the landscape, such as a valley bottom. And values near 0 are regions of constant slope. And apart from the elevation values themselves, the size of the neighborhood or the size of the moving window greatly impacts the TPI's calculation. And it's a trial and error process to choose the appropriate neighborhood size of your window. And this is a flow chart that shows the relatively simplified classification procedure where bathymetry data was used to derive slope and topographic position index, which were then used to classify slope zones. And bathymetry data came from JEBCO's 2019 product, since it covered the entire study region of the eastern EEZ in the United States, and because it had a coarse spatial resolution. Okay, now what we're seeing here are 5 snapshots of the same location, which is off of the Georges Bank, off of New England, and it's showing the 5 different topographic position index grids that were created from 5 different neighborhood sizes, where the neighborhood size is showed in meters, and the size increases from left to right, and then from top to bottom. And as we can see, as the neighborhood size increases, those positive, negative TPI values get stretched over larger regions. Those 5 TPI surfaces were then classified into 4 slope position classes, which were depressions, or regions that are lower in the landscape, crests, regions higher in the landscape, regions of flat regions, and zones of constant slope. And again, as you can see, as the neighborhood sizes increases, so do the size of the features. This next map shows slope zones that were classified from the second largest neighborhood size, which was 23,000 meters. And as we can see, the continental margin is well represented. However, those crest and depression features are exaggerated in size, and the zone of constant slope is not well represented, which is in orange. But you can't really see the orange because it's not well represented. Okay, and this next map shows the zones that were classified from the second smallest neighborhood, which was 4,500 meters. And the sizes of the depressions and crests more accurately reflect the underlying data. And the slope zones are represented. However, if we look at off the coast of the Carolinas, the continental margin is not well represented, since this map is showing that it's all flat when that is not true in reality. And the takeaway is that there's no definitively correct topographic feature map that can be derived from a digital elevation model. However, using derivatives such as TPI and other metrics, slope position zones and other seafloor features can be classified to fit a specific research goal, such as deep-sea coral habitat analysis. And to sum it all up, deep-sea coral and sponge data was enriched with the Global Seafloor Geomorphology feature set that can be disseminated by the deep-sea coral research team so that people can use for habitat analysis. And then slope position zones were classified for the eastern US EEZ. I hope this data can be used to help develop more effective conservation strategies. Thank you.